In the last video, we saw how the CPU switches between processes. And we also saw that sometimes the system decides to switch between multiple processes. But that raises a very important question. If there are multiple processes ready to run, how does the system decide which one to pick? That decision is made by something called the scheduling policy. A scheduling policy is simply the logic that decides which process runs next. Now here's an important idea. The CPU doesn't schedule entire processes at once. Instead, it schedules something called CPU bursts. A CPU burst is the time for which a process runs continuously on the CPU before it either blocks for I/O or finishes execution. So you can think of it like this. A process runs for some time, then maybe waits for disk, then comes back again. Each of those running periods is a CPU burst, and the scheduler decides which CPU burst to run next. Now, what is the scheduler trying to achieve? There are a few important goals. First, we want high CPU utilization. That means we don't want the CPU to sit idle. Second, we want low turnaround time. That is the total time from when a process arrives to when it finishes. Third, we want low response time. This is the time it takes for a process to start running for the first time. This is especially important for interactive systems. Fourth, fairness. Every process should get a chance to run. And finally, we want low overhead. Switching between processes takes time, so we don't want to switch too frequently. Now let's look at some simple scheduling algorithms. We'll start with the simplest one, first come first serve, also called FIFO. In this approach, processes are executed in the order they arrive. So if process A comes first, then B, then C, the CPU will run A completely, then B, then C. Simple, right? But there's a problem. Imagine process A is very long and B and C are very short. B and C will have to wait for A to finish. This is called the Convoy effect. And because of this, turnaround time becomes very high. So while FIFO is simple, it's not very efficient. Now let's look at a better idea. Shortest job first, or SJF. Here, instead of picking the first process, we pick the process that will finish the fastest. So shorter jobs run before longer ones. This actually minimizes the average turnaround time. In fact, it is provably optimal when all processes arrive together. But there's a catch. SJF is non-preemptive. So once a long job starts running, even if a shorter job arrives later, it has to wait. So short jobs can still get stuck behind long ones. To fix this, we move to a preemptive version. This is called shortest time to completion first, or STCF, also known as shortest remaining time first. Here's the idea. At any point, we always run the process with the least remaining time. So if a new shorter job arrives, the CPU immediately switches to it. This improves response time significantly, but it also increases context switching. Now let's look at one of the most widely used algorithms, round robin. In this approach, every process gets a fixed time slice, called a time quantum. The CPU runs a process for that time. If it doesn't finish, it is paused and moved to the back of the queue. Then the next process runs. This continues in a cycle. Round robin is preemptive. It is great for fairness, and it gives good response time because every process gets CPU time quickly. But there is a trade-off. If the time slice is too small, we spend too much time switching. If it's too large, it behaves like FIFO, so choosing the right time slice is very important. Now, all these algorithms are simple models. Real operating systems are more complex. For example, systems like Linux use something called multi-level feedback queues. Here, processes are placed in different queues based on priority. Higher priority processes run first, and priorities can change over time based on behavior. But don't worry about that right now. We'll cover it in detail later. So to summarize, the scheduler decides which process runs next. Different algorithms make different trade-offs. Some focus on fairness, some focus on performance, and some try to balance both. But so far, we've been looking at processes as if they are completely independent. In reality, that's not always the case. Sometimes processes need to work together. They may need to exchange data, coordinate actions, or communicate results. But here's the challenge. Processes do not share memory by default. So how do they communicate? That's exactly what we'll explore in the next video. We'll dive into something called inter-process communication, or IPC.